Welcome to our Milestone Educational webinar series. My name is Roberto Federico, and I'm the product specialist for Mercury Analysis line. Today's presentation is entitled Direct Mercury Analysis for Power Generation and Petroleum Refining. Before we get started, I'd like to go over the topics we will cover today. We'll be starting with a discussion on why mercury analysis is a relevant parameter in combustion-based power plants and the petrochemical industries, followed by which techniques have been traditionally available for its determination. We'll go over the operational principle behind direct mercury analysis and how this technique is applied for the determination of mercury in coal and crude oil samples. And then we will end with specific instrumentation features that you can take advantage of with direct mercury analysis for an easier operation. If you have any questions during our presentation, you can submit them anytime. At the end of the webinar, we will have a dedicated Q&A session to answer some of these. So why is it important to monitor mercury in these industrial processes? So as we know, mercury is a ubiquitous element in the environment. Short and long-term exposure has known toxicological consequences, and this exposure is increased by human activities. In the case of coal-fired power plants, combustion of raw materials for power generation is a known source on mercury emissions to the atmosphere. As a matter of fact, taking as a reference 2005 statistics, 50 tons of mercury are released every year from this activity alone. The EPA's Clean Air Mercury Rule was placed since then as an effort to regulate this, which has now turned into the current mercury and air toxic standards. An analogous framework exists for petroleum refining processes. Most crudes range within 2 parts per billion of mercury, but it can go all the way up to 100 ppb, depending on its source. Refining processes can result on releasing mercury to the final products that are being produced, to the waste, and also to air. So this is why it's critical to understand and analyze the mercury content in the raw materials involving the process to prevent its further transfer down the line and eventually to the environment. Among conventional mercury detection techniques, we have cold vapor atomic absorption spectroscopy, and we will talk about it in more detail, but it's worth mentioning now that this is a quintessential technique for mercury since it overcomes some of the issues that are particular for this element. It's a sensitive method with a wide range of detection. Those samples that are solid, though, do require a sample preparation step prior to its analysis. Some of you might be routinely performing plasma spectroscopy analysis with ICP-OES or ICP-MS. There are inherent advantages of ICP techniques in general. It's a multi-element method, which allows for the detection of many metals, and it provides excellent sensitivity. However, oftentimes when it comes to mercury detection specifically, there are known issues such as memory effects that increase the cleanup and maintenance of ICP units. As I mentioned, I want to revisit in detail the theory behind cold vapor atomic absorption, since it is a recurring technique within some of the standard test methods in this industry. For analysis of solid materials, the first step is sample digestion to release the mercury species from the matrix into a liquid solution to be analyzed. These mercury species are then reduced to its elemental form by means of a strong reducing agent, such as stannous chloride or sodium borohydrate. When the digestate is in contact with a solution of reducing agent, elemental mercury is generated. Mercury is then carried to an atomic absorption detector where it is measured and quantified. Along this sequence, there are wet chemistry steps that involve the use of additional reagents, the most obvious being a number of acids required for sample digestion, but also the ones involved in the reduction process of the reaction chamber, such as stannous chloride we mentioned, but also potassium permanganate to mitigate the effect of certain interferences. This leads to liquid waste generation that needs to be managed accordingly, but overall the main effect is increasing the time required for analysis. So having an alternative that overcomes these issues was the motivation behind developing a solution for mercury determination. Milestone first launched its direct mercury analyzer about 20 years ago and it has recently released its 7th generation DMA80 EVO. The DMA80 EVO, in contrast to the techniques we reviewed, does not require any sample preparation. This saves time and reduces the potential loss of mercury during the process. Also, you can analyze solid, liquid, or gas samples within 5 to 6 minutes. The DMA80 EVO incorporates several features that we have improved and added throughout the years in our experience as the market leader in direct mercury analysis, with more than 2,500 systems installed worldwide. The extent of how eliminating sample prep in the overall process is shown in this graph. Most of the time dedicated to analysis by CVAA consists on getting that mercury into solution rather than the actual detection step. This includes the time for digestion, calibration, and preparing the solutions that are needed for the process. In contrast with direct mercury analysis, getting mercury into its elemental form is built into the sample run in a way that you can get a result after 6 minutes of loading your sample. It is this feature, the one that takes a toll on the differences in productivity and costs that you can get with one technique or the other. We will be discussing this in more detail later in our presentation too. All right, so let's look into the performance of the direct mercury analysis. So I want to first address this by going over the principle of operation behind direct mercury analysis. And there are 3 main distinctive steps. The first one being thermal decomposition, followed by a catalytic conversion, then a mercury amalgamation, and finally atomic absorption detection. Best way to do this is by providing a short video where we go over this. So we start by loading the sample on a sample boat. The ones shown here are made of quartz, but we also have nickel boats available for solid samples. There is a 40 position auto sampler where the boat is picked up, then it's placed inside a thermal decomposition furnace. Here the sample is heated and all the mercury species are released from the matrix, including ionic ones that are transported to the catalyst by the carrier gas. Once in the catalyst, all of these will be converted to elemental mercury, then they're retained into the gold amalgamator. And after that, the mercury is flash heated, going to the double beam atomic absorption spectrophotometer, where we measure mercury and quantify it. So since the thermal decomposition step releases all mercury, regardless of which matrix it comes from, you can use liquid standards to create a calibration curve. There are different ranges of detection, each one corresponding to a different cell within the spectrophotometer. The software automatically assigns the calibration that corresponds to the mercury amount present in the sample. Also, once you calibrate, you do not need to do it on a daily basis. The calibration has a long lifetime, as evidenced by the results of daily verification checks. So we have a better understanding of how direct mercury analysis works, but how does it perform for specific raw materials in the power generation process? Let's start by looking at its performance for coal and coal combustion residues. So the standard method that describes the procedure for mercury determination by direct combustion analysis is ASTM D6722. Most of our users in contract testing labs follow this methodology, which includes this principle of operation as a technique of choice with the 4 steps that we just described. A step prior to loading the sample into the nickel boats is to pulverize it and pass it through a 60 mesh sieve. This homogenizes the particle size, improving recovery, and also contributes to more precision across replicates of the same samples. This is valid for the actual samples. Typical sizes used for this method go up to 250 milligrams. Here is a list of the operational parameters used for mercury determination in coal. Most of them are standard across all methods used in the DMA, and there is no adjustment needed by the user. The one that is critical in improving the recovery of mercury and is different from the method used for most samples is the decomposition hold temperature. Instead of the default 650, the temperature is taken to 750 degrees Celsius to release all the mercury from the matrix. Since these are dry samples, a single ramp is used to reach this final temperature. So here we have an example of the performance of direct mercury analysis in coal-related samples. On the left, we have two commonly used solid reference materials in this field. The first one being SARM-20 coal, and the second being NIST 1633B coal fly ash. These tables are the average results for a series of 5 replicates on which we can observe that the standard deviations obtained are within the reference value and its reference variability. Also, each individual result is within 10% of the certified value. The samples here on the right are 5 unknown coal samples provided by a coal-fired power plant. And the sample size used for the analysis was within the range of 90 to 250 milligrams. The mercury levels found are consistent with the expected ones for this matrix, and its accuracy can be validated by the CRMs run throughout the analysis. But it's also worth mentioning that the standard deviation of shown here for 4 replicates each is minimum, considering that the coal samples are notorious for not being homogeneous. So now we move on to analyze the performance of direct mercury analysis in liquid hydrocarbons. And here we take as a guideline UOP method 938, which is one that would be frequently used in regulated environments such as testing labs. This method references a specific manufacturer on the text of the method. However, the underlying principle of operation we have discussed so far, which includes thermal decomposition, catalytic conversion, amalgamation, and atomic absorption detection, falls within the description of this method, making the DMA 80 suitable for its analysis as well. An important methodology change that is particular to this method is the use of additives during analysis to mitigate the effects of certain interfering species that can reduce the lifetime of the catalyst. There's our additive B that counteracts the presence of halides in the sample, which is an aluminum oxide-based material. For those samples with known sulfide content, a mixture of calcium hydroxide and sodium carbonate can be used in tandem to remove the effect of this interference. Both of these additives need to be exposed to the same thermal decomposition procedure that the samples to guarantee that there is no mercury present. An additional effect they have is to provide a large surface area to control the combustion of hydrocarbons within the chamber. Remember, we are dealing with highly volatile and reactive samples. Following up on this, the recommended carrier gas is compressed air. Combusting these samples is definitely not a problem, and limiting the amount of oxygen by using air instead assists to control the thermal decomposition process. So here's an example of how a certified reference material is processed, specifically NIST 2722 heavy sweet crude oil. The picture on the right reflects how this sample is loaded to the boat. Not necessarily shown here, but there is a bed of the additive underneath and the oil sample is placed on top of it. Here we have 5 replicates of NIST 2722, all of them falling within the certified range of 0.129 plus minus 0.013, indicating a reliable recovery during the analysis. So on the left here, you can observe results for the analysis of 4 crude oil samples with the DMA 80. The statistics here are for 5 replicates of the same sample. All of them are coming out at less than 2 parts per billion. You can see that the relative standard deviations for these are within 15 to 10% and below. And this is typical and expected for very volatile samples at these concentration levels. To validate the accuracy of this analysis and the complete recovery from the matrix on the right, we have the same series of samples with a 1 ppb spike, all of them with recoveries between 95% and 105%, and relative standard deviations within the expected ranges. So now we already know how direct mercury analysis works and how it can perform in analyzing matrices within coal-fired plants and petroleum refining processes. I want to revisit in more detail the comparison we made earlier on regarding the differences in productivity between the 2 techniques. So take a look here the side-by-side comparison between the two. The first item being the calibration during analysis. You'll need reference material for both and daily verification for both as well. However, for cold vapor atomic absorption, you do need to perform a daily calibration. Factoring this in and including that the time needed for digestion, it takes about double as much time to process samples with CVA8 than the DMA. If you take an 8-hour workday, DMA lets you process 80 samples per day compared to half of it in cold vapor, which means that the labor cost per sample is cut in half for direct mercury analysis. But also remember, we're not using new solutions on a daily basis, considering the cost on consumables per sample. This represents the fraction of the reagent cost with cold vapor. So tallying all these factors, you're looking at a 70% cost savings when you compare direct mercury analysis versus CVAA, mainly because you're not calibrating daily, you use less reagents. This leads to a faster process and more samples per day. So we talk about general performance of the DMA80. Now let's go into some of the specific features that makes this instrument and technique easy to use from an operational standpoint. A very useful feature with the DMA80 is auto blank. We talk about how mercury is notorious for its carryover issues. So on top of limiting this effect with the hardware design, we have also included an auto blank feature to help avoid overestimation of concentrations during the run. This way, you do not have to worry about reprocessing a sample batch if your blanks are higher than needed. So take this situation as an example. We have a sample with very high mercury levels on the left. After this sample is processed, instead of running the next sample and risking having added mercury to that result, the system runs an instrument blank to confirm no mercury is present. If the mercury amount surpasses a predetermined level, it runs a second blank until the background levels are low enough to avoid any interference. You can adjust the mercury limit on the high end to trigger the auto blank cycle, and you can also adjust what the blank level should be before picking up the next one. When it comes to the use of the DMA80 software, we have incorporated several features that makes the overall operation easy to use. For regulated laboratories, it is 21 CFR compliant and can be connected to the LIMS. It also allows for importing and exporting, post-processing your data, and setting custom auto blank limits as we just discussed. As far as import and export capabilities, you can either generate a CSV or PDF file of your samples, your methods, or your calibration. Conversely, you can load the information of a full batch in an Excel file and load it to the software to start a full run. For situations when you want to rename a sample or you want to compare different calibration files, this software allows you to reprocess the data without having to reanalyze the same sample twice. This is a feature added specifically on the latest DMA80 Evo. Also, a very convenient advantage is having the capability of connecting your balance directly to your DMA80 terminal controller. The software is compatible with a number of manufacturers. When you weigh the sample, you can see real time when the reading stabilizes in your controller. Once you get your mass reading, you accept it and the value is entered automatically. Alternatively, you can enter the mass manually as well. As I mentioned, for contract labs or any other heavily regulated environments, the system is 21 CFR compliant. You get a history trail of any changes performed within the system, in addition to different levels of access from user, manager to supervisor or administrator. Finally, the system can be supplied with either a terminal controller or laptop controller. Either one has the same features and user interface that we just described. Which one to use is ultimately depending on the user's preference. So another feature from our DMA80 Evo is the use of our web app Milestone Connect. This is a unique app to Milestone. It allows you to remotely monitor the instrument real time by connecting the same user interface that you will have access to in the terminal controller to a PC or a tablet or a smartphone. It also gives you access to many of the application notes, some of which are the ones where we had the data that we discussed today. Also scientific papers, user manuals, tips and techniques, and any other resources for the regular operation of your DMA AE. You can also access the application's team and reach us out directly, and you can order parts and consumables as needed. These are some of the examples for those application notes and reports that are pertaining to the application that we discussed today. But you can also find several other topics on these kinds of resources. So I just want to recap and provide some of the main points that we discussed today. Before I do that, I'll go ahead and submit a poll in case you would like to receive more information regarding the DMA 80 EVO and potentially have a virtual demonstration or connecting with an applications team specialist to learn more about your particular needs. As I mentioned, the direct mercury analysis allows for fast and accurate techniques, for fast and accurate results for coal and petrochemical analysis. It's easy to use. There's no sample prep required. And it enhances the productivity compared to traditional techniques, both in terms of cost savings, but also by increasing the productivity of your lab. Well, thank you again for joining us today. At this point, I'll go ahead and review if there's any questions from our audience. All right, just a second here. Okay, so one question is, what are the consumables? And I know I discussed this or briefly mentioned it, but didn't really go into more detail. Consumables for the DMA 80 or direct mercury analysis in general are the catalyst tube that we showed on the animation on the principle of operation, and also the amalgamator. After a while, once you start processing a number of samples, the catalyst will start losing its sensitivity, so you need to replace it every so often to make sure you stay within the optimal sensitivity range of your instrument, and you can really take advantage of the limits of the low detection limits that likely your application requires. Do you need to use it in a fume hood? You don't need to use it in a fume hood. It probably wasn't as clear in the animation there, but at the end of the path of mercury, once it leaves the spectrophotometer, there is a final step where it reaches a carbon-based sorbent trap. That way, all the elemental mercury that was already analyzed is absorbed onto the surface of that trap rather than needed to be exhausted and creating more emissions or waste. So no, you do not need an exhaust line or to operate it inside a fume hood. Let's see. Another question is, what are the limits of detection for the instrument? So this will depend. I also did not go into detail here, but there are 3 different configurations that we have available for the DMA. That being the wide range, dual cell, and tri-cell. Dual cell and tri-cell are the ones that are more suitable for these kinds of applications. Taking the tri-cell, you can achieve, depending on the sample matrix, down to single-digit ppb or less. Dual cell will be more along the lines of 10 nanograms and above. So it's ultimately depending on what kind of matrix you're dealing with, but you can definitely, in terms of total amount of mercury that can be detected, you can be looking at less than 0.1 nanograms of mercury in a single sample. All right, so we want to limit this presentation to, I guess we have time for one more question here. It's okay, so how to analyze gas samples. So I mentioned that you can analyze gas samples as well. The way that we do that is not by directly injecting the gas into the stream of the flow of the instrument. We have dedicated sorbent traps where you can sample either pressurized gas cylinders or ambient air, whatever the application is, and you measure how much gas passes through that sorbent trap with a mass flow controller. and that same sorbent trap is placed directly onto the tray or the 40 position auto sampler. It's outfitted for that exact size. And that way you process it as a normal solid sample with the same thermal decomposition method. All right, thank you everyone for joining us today. Any other questions that were not answered here, we will follow up online. And we are developing continuously more webinars regarding our offering and our product lines. We hope that you can join us on those once we have those in place as well. Thank you so much. You have a good day.